Hello everyone, my name is Neha Makwana. I am an assistant professor at Aditya Silver Institute of Technology, Silver University. Today I am going to explain the concept about complex numbers. So, these are the outlines of complex numbers, definition of a complex number, conjugate of a complex number, modulus of a complex number, power of quota, sum difference product division of complex numbers, geometrical representation of a complex number, and we are going to understand all these outlines one by one in detail. First of all, let us see the definition of a complex number. A complex number is a number that can be expressed in the form a plus ib, where a and b are real numbers and I is the imaginary unit. Generally, the complex number is denoted by capital Z, and the set of complex number is denoted by capital C, where A plus IB and A and B are real numbers. The set of real numbers is a subset of complex number. Now let us understand and let us explore the complex number system. But before that, let me recall the number system. We know that all the positive integers are considered in the set of natural numbers. If we include 0, then 0 and all positive, that is what is the set of whole numbers. Then 0, positive and all negative integers are there in the set of integers. And then rational numbers. We know that all fractions and decimals are rational numbers. So rational numbers are numbers which we can represent in the form of P upon Q, where we know that P and Q are integers and Q is not equal to 0. And the numbers which we cannot represent in the form of P upon Q or as fractions or decimals, that is irrational numbers. Like root 2, pi, e, all these are irrationals. And rationals and irrational together makes the set of real numbers. So we can say that natural number is a subset of whole number is a subset of integer is subset of rational numbers, and rational numbers and irrational numbers, the union of both of them makes a set of real numbers. And now we have learned about the complex numbers. So all real numbers are complex number because the imaginary part is 0. And now we also know that we have also imaginary numbers. So real part and plus imaginary part, it will make complex number. So this is what is complex number system. Now let us try to understand the conjugate of a complex number. Suppose we have given any complex number z is equal to a plus ib. So here a is the real part of z and b is the imaginary part of z. So the conjugate of a complex number is defined like z is equal to a minus ib. That is what is conjugate of complex number. So if we can say that if two complex numbers differ only in the sign of the imaginary part, there is only the difference of sign in the imaginary part. Let us see some example of it. 3 plus 4i. So what will be the conjugate of 3 plus 4i? It's 3 minus 4i. Only the sign difference in imaginary part. Here 4i is the imaginary part. And conjugate of minus 4 minus 7i is minus 4 plus 7i. Remember, here real part will be as it is. Only the difference in sign in imaginary part. Here we have 5i. So 5i we can say that it is purely imaginary number because here the real part is 0. So, conjugate of 5i is minus 5i and conjugate of 6 is 6 because uh, here 6 we can write as 6 plus 0i. So here we have b is equal to 0. So here imaginary part of this real number, this complex number is 0. So, uh, in conjugate we have to just prefer the sign in imaginary part. So here uh, uh, conjugate of 6 is the same as 6 minus 0. I see. Let's see. Now let us discuss the topic modulus of a complex number. So the modulus of a complex number z is equal to a plus ib. It's denoted by modulus of z. Also we can say it as absolute of a complex number and is defined as square root of a square plus b square. Suppose we have example, suppose we have one, for example, let me have one complex number minus 5 plus 4i. So here, the real part of this complex number is minus 5 and imaginary part is 4i. So if you want to find the modulus of this, we have to just do the square of a and b. So minus 5 square plus 4 square, that is square root 41. The modulus of a complex number is a non-negative real number and represents the length of the vector corresponding to the complex number in the complex plane. So in the complex plane, to measure the distance between points, we have this modulus of complex number and the formula is under root a square plus b square. Because distance can never be negative, so we have the sum of two square numbers. Now let us discuss the powers of quota. Here in the set of real numbers, we know that negative numbers do not have square roots. So imaginary numbers were invented so that negative numbers would have square roots and certain equations would have solutions. So these numbers were devised using an imaginary unit named I. So here in complex number, we imagine that there is one number and a number whose square is negative is said to be imaginary number. An imaginary number known as quota. So here I is equal to square root minus 1. The value of I is equal to square root minus 1. The imaginary number consists of all numbers vi, where b is a real number and I is the imaginary unit. So with the property that I square is equal to minus 1. We have to remember that I square is equal to minus 1. The first four powers of I establish an important pattern and should be memorized. So here you can see I raised to 1 is equal to I square minus 1, I cube minus I, and I raised to 4, 1. Here, if you want to measure the powers of I, what we have to do, we have to divide the exponent by 4. So if there is no remainder, then the answer is 1. If remainder is 1, then answer is I. If remainder of 2, answer is minus 1. Remainder of 3, answer is minus I. We can also remember if power of I is equal to 2n and if n is odd integer, then answer is 1. If n is even integer, then answer is minus 1. If I raised to 2n plus 1 and n is odd, then answer is I. And if n is even, then answer is minus I. Let us calculate this powers of I23, it will be minus I raised to 2006 will be minus 1. I raised to 37, that is I raised to 828. So even, so 1. Here, we can express these numbers in the terms of I, because here we have square root of minus 5. Okay, so my B is 5, and 5 into minus 1, that is minus 5. So here, under root minus 1, I can write as I. So I root 5. Similarly, we can write minus under root minus 7 is minus 1 into 7. So we can write it as minus I root 7. And minus under root minus 99, we can write it as I under root 9 into 11. So we have 3I under root 11. Similarly, we can write like this. Here, 36, square root of 36 is 6. So we can write it as minus 6I. Here, 16. So square root of 16 is 4, and 160 is 14 into 10. So 4I root 10. Then let us see how to multiply 2I into under root minus 5. So we have 2I into I under root 5. So here, this minus under root minus 5 we have written as under root minus 1 into 5. Minus 1 under root minus 1 is what equal to I. So I square. And we know that I square is equal to minus 1. So we have minus 2 under root 5. So in this way we can multiply. Similarly, we can see here we have 2I. So we can write it as I square. I square is equal to minus 1. So we have final answer square root 21. Now let us discuss the sum, difference, product and division of a complex number. The sum of two complex numbers. If we have two complex numbers, a plus bi and c plus di, so if you want to do sum of it, what we have to do, we will add the real part of, first of all, we will add the real part of it, and then we will add the imaginary part together. And similarly, we can find the difference between two complex numbers. First of all, we have to find the difference of two real parts and then of imaginary parts. In imaginary part, I will be common. The product of two complex numbers, a plus bi and c plus di, we can calculate this multiplication by using the distributive property of multiplication. We will see some examples of all these operations. Now let us see how to divide two complex numbers. Okay, suppose we have two complex numbers a plus bi and c plus di. So what we have to do, we have to multiply the numerator and denominator by the complex conjugate of the denominator. So if we multiply the denominator by complex conjugate, then we can use one algebraic identity a square minus b square. And because of that identity, when we multiply both the complex numbers, and if we get I square, then we know that value of I square is equal to minus 1. So our denominator will be rational. Any real number we get then. So let us do all the operations. First of all, let us see how to add or subtract. Like 7i plus 9i, they are imaginary parts. So their answer is 69. 5 minus 5 plus 6i plus 2 minus 11i. So first of all, we will add real part. Minus 5 plus 2, that is minus 3. And 6i minus 11i, that is minus 5. So first of all, we will add or subtract the real part and then imaginary part. Let us see example of subtraction. 2 plus 3i minus 4 plus 2i. Subtract real part 2 minus 4. First of all, we will open the bracket. So here, this real part 2 minus 4, that is minus 2, and imaginary part plus 3i minus 2i, that is plus 9. Now let us learn how to multiply. Here, let us multiply minus I. We will open the bracket. So I multiply with 3 and then I with I. So I square will be minus 1. So our final answer is minus 3i minus I square, and we know that my I square is equal to minus 1. So our final answer is 1 minus 3i. Now let us multiply 2 plus 3i minus 6 minus 2i. We will open the bracket. First, we will multiply 2 with all this bracket, minus 6 minus 2i. So we have minus 12 minus 4i plus 3i with all the bracket, minus 6 minus 2i. So we have 6 3s are plus minus minus 89 minus 6i square. And we know that I square is equal to minus 1. So we have minus 12 minus 20i minus 6 minus 1. So our final answer is minus 6 minus 20i. Now let us see one example of division, how to divide complex number. We have given one complex number 3 plus 11i upon minus 1 minus 2i. So to divide, we know that we have to multiply and divide by conjugate of its denominator. Here our denominator is minus 1 minus 2i. So conjugate of this is minus 1 plus 2i. So we will multiply and divide it by conjugate, which is minus 1 plus 2. Let us open the bracket and simplify it. So we have this. We will put the value of I square that we know, minus 1. So minus 3 minus 5i plus minus minus 22 upon 1 plus 4. So for final we have minus 25 minus 5i upon 5. Now minus 25 upon 5 minus 5i upon 5. So our final answer is minus 5 minus I. Now we will discuss the geometrical representation of a complex number. Before that, let us see the complex plane. In complex plane, we have real axis and imaginary axis. Our x-axis, horizontal is real axis and vertical line is imaginary axis. So, in a complex plane, our number, complex number a plus bi, we can represent geometrically as a point. So, where our x-axis is the real part and y-axis represent the imaginary part b. And we have to find the magnitude. Magnitude, that means the distance from the origin to the point. So that is what is distance between these points. We will gonna calculate. And that is what is absolute value, or also we can say modulus of a complex number. And then we have the angle theta, which will form with positive real axis. And it is said to be the argument or phase or amplitude of the complex number, which we can calculate by theta is equal to tan inverse b by a. Let us see how to graphing the complex number in the complex plane. We have real axis, imaginary axis, 0. We know that their intersection point is 0. Here we have 2. Denote this complex number minus 2 plus 5i in the complex plane. So here our real number is minus 2. So minus 2 will be here. And in imaginary part of a B is 5. So it will be here. So our point will be at here, and we will calculate the magnitude. We can see this distance is 2 from the origin, and this distance is 5. So our magnitude we will calculate by using the modulus formula. So in this way, we can represent the complex number in complex plane. Let us have some examples of graphing in the complex plane, sum of complex numbers. Let us see. -2 plus 5y, 2 plus 2y, 4 minus 3y, and -4 minus 3. So -2 plus 5y lies in the second quadrant. Here, 2 plus 2y lies in the first quadrant. 4 minus 3i in the fourth. And -4 minus 3i in the third quadrant. So, this is the geometrical representation of the complex number. So, we know that there are too many applications of complex number and theory, complex analysis, which is used in electrical engineering, quantum physics, and signal processing. So, I hope this complex number, there are many applications of it. Thank you very much.